Hello, hello, hello. Welcome to XC Psychology. Today, we're going to try to answer the question, why doesn't everything just mix together? Actually, they do, just not evenly. To start, let's recap last episode's key concept, diffusion. So, if we look at image 1 here, we have a lot more particles on the left side and a fewer on the right side, right? That's the starting point. At image 2, we see that more particles move to the less crowded side. At image 3, we see the number becomes even. The particles are still moving, but now they are, you can say it's mixed, and it's more or less evenly distributed. And so this is a key concept in neurobiology called concentration gradient. It is the difference in the amount of a substance across a distance, moving from high concentration to low concentration. If you remember, we also talked about the sodium ion in our digestive system last episode. So remember, concentration gradient is the difference in the amount of a substance across a distance, the moving from high concentration to low concentration, right? Here's a difference, right? Across the distance from high concentration to low concentration. And what happens after it's evenly distributed? This is what we call the dynamic equilibrium. The particles are still moving, but the balance stays the same. If we look at the word equilibrium, it's a state of balance. It is from two Latin words. Equus, meaning equal, level, fair, or even, and libra, meaning a balance, a set of weighing scales, or a pound weight. This is a root for the astrological sign Libra. Equilibrium, this word entered English language around 1600s. So we can understand dynamic equilibrium as dynamically balanced. So if you remember from our last episode, we have this example of food dye enters into glasses of water. And from a molecule level, we can say at the beginning, it is not evenly distributed and molecules are always moving. That is discovered by Robert Brown in 1827 and later proved by Albert Einstein about 80 years later. And we have the concentration gradient. So we're going to move from high to low, and until it is spread out, we have dynamic equilibrium reached, and there's no net movement. Right? But in neurobiology or in our body, things don't mix evenly. They do mix, just not evenly, because it will create problems for our neurons. And our neurons create or intentionally maintain a concentration gradient by using barriers, our cell membrane, our selective channels, like if you remember last episode, we talked about special channels that requires both sodium and amino acid, and some channels, if you learn later on, could only require sodium ion or potassium ion. We also have ATP channels, which we've discussed extensively in Module 1. And here is a brief illustration of uneven distribution or uneven mix. Usually our membrane resting potential, that means no stimulus has occurred, our body maintains a negative millivolt. So it's usually around -70, but depends on which type of cells, it may vary a little bit. And what does it mean is that there will be more ions on the outside, particular ions on the outside, and some particular ions on the inside. What does it mean by negative? If everything is mixed evenly, we'll reach to a 0 millivolt, no? So the fact that we maintain negative millivolt, that means we have more positive ions outside and more negative ions and particles inside our neurons. And that is an intentional design of our body. Please watch Module 1, you will find out your answers. So today's video is relatively short, but focused. The key takeaway is a little bit philosophical. Life depends not just on movement, but on preserving the differences that matter. Our cells, our neurons, intentionally preserve the difference for concentration gradient to get ready to fire action potentials. And our DNA is only a single-digit percentage difference from gorillas. And that is also an intentional difference from evolution. Food for thought. So, coming up next, why don't eyes only follow concentration?